All right, video 2 for lesson 5.2. Let's continue on with the angle bisectors. So now we're going to talk about the concurrency of angle bisectors, right? So it says that the angle bisectors of the angles of the triangle are concurrent, and they're going to be equidistant from the sides of the triangle. All right, so not from the corners, but from the sides. So in this picture here, we have 3 angle bisectors. We have this one here, J, this one here, K, and this one here, L. So J, K, and L. You can see that it has bisected the angles. Notice that when you draw a segment from this point of concurrency perpendicular to each side, remember, equidistant, a point to a segment or a line has to be the perpendicular segment. So this length represents the distance from Q to each of these sides. Notice they're all the same, right? This is 2.5, that's 2.5, that's 2.5. So again, in this picture, Q being that point of concurrency, Q to M equals Q to N equals Q to O. Q to the side are equidistant. Okay, so let's investigate inscribed circles now, right? So now we want to construct a circle, but now we want it to be, inside the triangle so that it intersects each side at exactly 1 point. So the term for this is tangent. When a circle intersects a side at 1 point, exactly 1 point, it's called tangent. We're going to do this in topic 10. When we talk about circles. So we got a little bit of time, right? But this idea of intersecting at 1 point is called tangent. So it says here the circle that intersects each side of a triangle at exactly 1 point, it has no points outside the triangle, is the inscribed circle of the triangle. It's inscribed in the triangle. Okay? So you'll notice here, right, this point right there, that is going to be the center of your circle. We call that the incenter. And again, it's the center of the inscribed circle. And then these 3 lengths, the distance from the incenter to each of the sides, is congruent, so it's going to be the radius, right? It's going to be that constant length that helps make the circle. So again, in the last picture, these were the corners A, B, and C. This was Q in the middle, and now we have our points M, N, and O that we are equal distance from. So again, this point of concurrency is called the incenter. Right? Again, it's the center of the inscribed circle. Center of the inscribed circle. Okay, so again, let's take a look at how Savas is going to construct this, and then we'll do it ourselves in Desmos geometry. Okay, so here are the steps here. Let me slide this to the side so we can see those steps clearly. Okay, so it says, first, construct the bisector of one angle. So there's step 1, bisector of one angle. Second, construct the bisector of another angle. So notice in all these problems, we never do all 3. If all 3 meet at 1 point, then 2 are going to be at that same point. So you don't need all 3. Okay, so now we can find the incenter. Good. Now we must find or construct a segment perpendicular to one of the sides. Use the side that is most convenient to you. Sure, they did it right here with the triangle. That's fine. This, again, is going to represent the radius of the inscribed circle. And now you use the center here, use where the perpendicular touches the side to measure out the radius, and you draw the circle. And you're done. Okay, so let's see if we can use some Desmos geometry to accomplish the same feat. Now, I will say this is a little more difficult because they don't have an angle bisector construction, so we kind of have to do it ourselves. So we're going to draw a triangle. Remember, you got to touch that first point last to create that triangle. So here's how we have to construct an angle bisector. So first thing we have to do is we have to draw an arc across the angle. So grab the circle tool. We're going to draw a circle down this angle like so. Now, we're going to use this as our compass. So I need to create a segment right here. Okay. All right. And I need to mark this point here. Okay. Now, unlike delta math, you cannot draw pencil arcs. So we have to mark these points. So now we're going to use more tools, the compass. Now it says choose a segment. I'm going to use the same circle size, so the segment is the radius. I'm going to choose that segment, and notice I have this circle, same size. I'm going to put it right here, and stop, right, and draw that circle. I'm going to do the same thing up at this point. Grab that segment, so more tools, compass, grab that segment, right there. Where those two circles intersect, pretend I made two arcs out there, that is going to be the second point on my angle bisector, and I will connect that corner with that point to create one of the angle bisectors. Done. And I will hide the circles. You can click and drag, so click the arrow, you can click and drag and click hide. And that should hide the circles. There we go. And again, if I move that angle, if I move that angle bisector moves with it. Okay, let's do the same thing over here. So let's grab the circle. Let's start at the corner and go down the circle. Let's mark a point where the circle hits the other side, and let's draw a segment right there. So now I have this segment marked. So now I'm going to use the compass tool. I'm going to choose that segment. There it gives me my circle. Put it on one of the points where the original circle crossed the side. Do the same thing. Click on the segment again and go to the upper point. Where those two circles cross right there, that's that point I need to create my angle bisector. Use array, start at the corner, connect to that point. There we go. And hide those circles. And again, if I move this top, see both angle bisectors move. Okay, so the point right here is going to be our end center. So I'm going to mark that as our end center. Let's see if I can spell it correct this time. In center. There we go. Nope. Forgot the E. Okay, in center. And now, to get the circle, I need to find a perpendicular from this end center to a side. So I'm going to choose more tools, perpendicular. I'm going to go to this bottom side just because of the way I drew it. It seems like it's most visually pleasing. So I click on that bottom side and then click on the end center. This is my perpendicular. This point right there is going to represent the radius. This length right here is my radius. So if I grab my circle, I click on the end center, click on that point, and there. Look at how it touches each side. It touches the tangential, I think is the word, right? Each of these touches exactly one point. And if I move these, notice that the circle moves with it and it stays tangent. Now notice here, this is an acute triangle, right? So notice the incenter is in the acute. Incenter's on the inside. If I try to make this angle a right angle, let's see what happens. Notice that that inscribed circle, that incenter, stays inside the triangle. And if I keep going and make it wider, again, it stays inside the triangle. So for the incenter and inscribed circle, it's always going to be inside the triangle no matter what shape the triangle is. All right, cool. We'll make sure to do those constructions in class or see if you can by yourself. Okay, so let's get back to our notes here. We have one more problem to do. It would be problem or example 5. This one says, identify and use the incenter if QP equals 3 times x plus 1 and RP equals 5x minus 3. What is the radius of the inside circle of triangle JKL? So up here, this right here is showing that angle K is being bisected. So KP is an angle bisector. This right here is showing that PL is an angle bisector. So because of that, the distance from K to P is, wrong theorem. The distance from P to Q, right? The perpendicular distance from P to Q is the same as P to R. So we're just going to take these two equations and set them equal to each other, right? So we know that Q to P is going to be equal to R to P. So QP is 3 times x plus 1 and RP is 5x minus 3. So we'll distribute. That's 3x plus 3, right? If you distribute the 3 in there, that equals 5x minus 3. I'm going to subtract the 3x to bring the x's on the right-hand side, keep it positive. 3 equals, that's 2x minus 3. I'm going to add 3 to both sides. 3 plus 3 is 6, equals 2x. And then I'll divide by 2. And I get an x value of 3. So they would like the radius of the inscribed circle. So again, if I draw the inscribed circle, it would look like this. This right here would be my radius, and I would draw it just like so. Pretty good. So QP or PR is that radius. So to find the radius, I'll just use QP, which would be 3 times x plus 1. You notice I replace x with 3. 3 plus 1 is 4. 4 times 3 is 12. So the radius is 12. And that's it. Oh, I should say the radius. QP is 12, so the radius equals 12. All right, thanks for watching. Good luck on your practice in class. See you then.